Hi, Sai. Thank you. My talk is about the depth of profiling Ruby. I just built a new Ruby profiler. Today, I'm going to share my journey and learnings from the experience. Let me introduce myself first. My name is Daisuke Aritomo. People call me Osoyu on the internet, so feel free to call me anyway, in either way. Also, I'm the member of the RubyKaigi NOC, which is the Wi-Fi team, so I've been running around the venue yesterday. So enjoy your connections. And I'm a big fan of pork tamago onigiri, which is this. This is Okinawan onigiri. I'm eating these like 3 times a week throughout the year. So I'm very much sure that I'm in the top 1% of RubyKaigi participants when it comes to these. And I have an advertisement today. The Smart Bank, which is a company I work for, is a hydration sponsor for RubyKaigi. We're giving out free drinks like this, like Coca-Cola, some bean tea, outside the large hall. So please stop by and grab a drink. Let's get back on track. What are profilers in the first place? The dictionary states that a profiler is a person whose job is to collect useful information about somebody or something so that they can give a description of them or it. What would this mean in the context of programming? A profiler in the context of programming is a tool injected into a program to analyze its performance. These are often used to reveal the hotspots, which is a code block that is making your program slow. The figure on the right is called a flame graph, which is a popular visualization that profilers create. It indicates the hotspots, the heavy methods, by representing time-taking methods with horizontally longer bars. So in this case, you'd like to look into the right part of the program to find why your program is slow. And today, I'd like to announce my new Ruby profiler, which is called PF2. I've been working on this for a while. PF2 is focused on analyzing Ruby programs from various points of view. Let me introduce some features. And its usage is very easy. You don't need to modify your code. All you need to do is append PF2 run before your Ruby commands to use it. So PF2 is capable of kind of classic profiling, which finds the time-consuming methods. And so it's in a flame graph, just like I introduced. So in this case, the string split function is taking a long time. Profiling multi-threaded programs was in mind when designing this. So in this case, the 4 tracks each represent a Ruby thread. So this is a program with 4 threads. The little bars in the middle indicates when the thread did actual work. A fun feature is that PF2 is capable of showing statistics of threads. So like how much time a thread spent in garbage collection doing actual work, how much time it wasted waiting for the GVL. So in Ruby, only one thread can use the CPU simultaneously. So it's important that to know if your threads are starving for the CPU. And based on this information, you can adjust the number of your threads if you're working on a web server. PF2 is also capable of profiling inside of C extensions, which is, I think this is only in my profiler. So one example of a widely used C extension is the MySQL2 gem, which is a MySQL2 client. So in case a bottleneck existed in the query function, it'd be kind of hard to know why your query is taking a long time. With the C extension profiling feature enabled, you get the blue part on the upper side, which represents the C stacks, which is under the underlying from the Ruby methods. So you can see that MySQL2 query method is built in mainly 3 parts: do send query, people, and read query results. Each represents sending the SQL statement to the server, waiting for the query, and receiving the results. So looking at this, you can understand why your query is slow, and it might be a hint to make your performance better. This feature also helps you finding hidden Ruby methods in Ruby programs. I've got a flame graph of the right side program. This is here. This looks quite normal, look like a normal flame graph, but actually some Ruby methods are not showing up here. Can you find them? The answer is this, the hash bracket function. Even though this method is actually consuming quite a lot of time, it doesn't get revealed in the Ruby flame graph. This is because if hash bracket is optimized in the C Ruby level and doesn't show up in the Ruby level stack trace. But if you have the C profiling feature, you can find the RB hash arrays, which represents hash bracket function. So if you have a little knowledge about C, you can get closer to the real bottlenecks of your program. Let's go to visualizations. PF2 offers several visualization modes supported by a visualizer called Firefox Profiler. Of course, there's the flame graph, and there's also the call tree view for this is like a tree view for the flame graph, and there's also the inverted call tree view. This is useful for finding methods so a single call doesn't take a long time. Instead, it's called so many times. You can find methods called a lot of times using the inverted call tree view. Why do we need so much features in a profiler? This is because bottlenecks often live in unexpected and unguessable regions. We programmers tend to think that we can at least guess where the bottlenecks are, but that's not true in many cases, especially when the bottleneck is not in our code. For example, I think spawning 50 threads in a Puma server wouldn't really make your server 50 times faster. This is because the limitations of the GVL. You need to know very well about Puma and the GVL both of them to guess the reason. But if the profiler knows of it instead of you, it can teach you. So building a profiler like this is not like in a normal Ruby program. And let's see how to do this. So the introduction is done. I'm going into the depth of profiling Ruby. Let's start from understanding the profiler's mission. A profiler's mission would be informative as possible. First, it needs to be informative as possible and never be misleading. It also needs to maintain low overhead because the profiler itself shouldn't be the bottleneck. If collecting too much information incurs too much overhead, maybe we shouldn't do that. And of course, it should be a friendly tool. Let's see how PF2 achieves these missions by looking into PF2's lifecycle. The profiler's lifecycle is split in 3 stages. First, the sample collection stage, which records the target program's execution state while it is running. Next, it runs, after the program ends, it does unwinding and aggregation, which is the stage about collecting additional information of samples. And finally, it does the visualization. Each stage has its own challenges. So let's start from sample collection. Sample collection. A sampling profiler collects samples every few milliseconds while the target program runs. Samples contain the execution state of the program. So like what Ruby method was running now, what was the underlying C function, did the thread have the GVL at the time? An understanding of the sampling profiler's timeline would help us. This diagram explains the life of a program, starting from main, and then the function A gets called. then B gets called, and so on. In this case, the profiler is configured to capture profiles every 10 milliseconds. So the bangs indicates a sample. The first sample capture comes when the program is running A. So the sample records the function main and A was running, and so on. So let's see how to actually collect samples. Well, collecting samples is the most fun part of creating a profiler. Profilers work by observing the execution state from the outside of the target program. Well, it is possible to observe that from inside a program, but I think all of you wouldn't want to wrap each method call with a time now and calculate elapsed time every time. Each type of information, like the running Ruby method, garbage collection, and GVL state, requires its unique approach. The most easiest way to collect these informations is to ask Ruby, because C-Ruby knows the best about the current C-Ruby state. It knows about the stack, threads, reactors, and garbage collection. Well, even many of them are not observable from Ruby code. In contrary, tools like perf wouldn't work without special support. This is because the Ruby stack is, well, we think it's the stack, but it's mere memory from perf's point of view. To do this, C-Ruby implements some useful APIs for profiling. There are 3 key APIs here: RB profile thread frames, the tracepoint API, and the thread events API. Let's examine each one. The first one is the most important, RB profile thread frames. It takes a thread as an argument and returns its stack trace. It's kind of, yeah. The return stack is represented as an opaque value, which is actually a pointer to the callable method entry, which we will abuse this later. To record garbage collection events, we use the tracepoint API. The tracepoint API is capable of reporting many events, including the garbage collection state, which is represented as a Ruby internal event, GC start and so on. So we use the tracepoint for collecting garbage collection events. While the tracepoint API is capable of returning method entries and returns, we don't use that because it incurs too many overhead. Finally, for the thread events API, we use it to observe the state of the GVL. The thread events API calls a hook when the thread state changes. So if we have a thread and it releases the GVL, it notifies the profiler through a hook. In this way, we can collect many information about Ruby. Now, this is a bit off topic, but querying the C-Ruby runtime is not the only possible method. It is possible to do sampling without runtime support by knowing everything about the runtime memory, what C-Ruby has in its stack, its heaps. If we can correctly reinterpret the C-Ruby's entire memory, in theory, we can know what C-Ruby knows. And there is a profiler called RB-Spy. It peeks into the memory and reinterprets it using a copy of all C-Ruby structs. But this is kind of off topic, so I'm not going to dig into this too much. So I've explained how to collect Ruby stacks, Ruby level stacks. So let's move our focus to C level stacks. This is needed for doing the profiling C extensions. As opposed to C-Ruby managed Ruby stacks, C level stacks are managed by the OS kernel. To do this, PS2 records the current CPU's program counter. Well, actually, it does this with the help of a library called libbacktrace. The program counter will be used later to restore the original stack trace. The important thing is that This process is done pthread-wise and will be matched with Ruby threads later. Now that we've seen what to collect, let's move our focus to when to collect. This process is called scheduling. Scheduling is about controlling when to collect samples. PF2's main strategy is to use OS-level timers. So in Linux, we use an syscall called timer create. This is a diagram which shows how timer create works. In this case, I have configured the profiler to fire. I have configured the profiler to capture events every 10 milliseconds. So when a thread has consumed 10 milliseconds of CPU time, the kernel sends a special signal, which is called sigprof, to the target thread. And PF2's signal handler will respond to it. In the signal handler, the sampling is done. Now, a scheduler for a good profiler should support multiple definitions of time. The most simple one is real time, which is time as we know, time as it flows in the real world. This is also known as wall clock time. Another one is CPU time. This is the amount of time which the CPU consumed in behalf of the entire process. And so this excludes time during I/O. So like if you're waiting for a SQL execution, a network, the hard drive, it doesn't count up for the CPU time. And the most interesting one is per kernel thread CPU time. This mode correctly reflects non-equal workloads. So if we have a very busy thread and a non-busy one, the profiler can control profiling timings for each one very accurately. Now, this feature relies on the fact that kernel threads can be linked to Ruby threads, so they can be one-on-one. We've seen that sampling happens in the signal handler. In signal handlers, it's very important to remember that very little operation can be done. So the most important part is that we can't do new allocations. I have designed the signal handler not to violate this. The collected data is kept into a pre-allocated ring buffer, and all the APIs we call is meant to be signal safe. So let's go back to the basics. Choosing the right sampling rate is very important for a sampling profiler. Of course, if we increase the sampling rate, we get more information, so we have more accuracy, and that means we have more overhead. PF2 chooses 19 milliseconds as the default. This kind of weird number, 19, why not 10 or 100 or 20? This is to avoid something called logstick sampling. So this is to not miss periodical events. If we have some other event, like checking something that runs every 10 milliseconds, a sampling profiler might run every single event, and that would produce a very incorrect profile. So it's important to choose a kind of weird sampling rate. Another important aspect is to control the overhead. Sampling always pauses the program. I have set the overhead goal to under 5%, so this means that we can use 950 microseconds for each round, which is 5% of 90 milliseconds. If we need to do more work, if it goes over 950 microseconds, we shouldn't do that. Some of you have noticed that this sounds much like systems programming, and well, it kind of is. So I chose to implement PF2 profiler, the profiler part, in Rust. I thought Rust was a very good language to do this. However, most code needed to be unsafe. So even though even though Rust is meant to be a safe language, I was always seeing seg faults. But still, the programming experience was quite good. So maybe some of you might want to implement a gem in Rust. So finally, I've completed the sample collection part. The second stage is unwinding and aggregation. PF2 collects minimum information during sampling. As I said, this is to make the capture process very low overhead as possible. This information does not contain file names and line numbers. So we need to symbolize and unwind the full stack trace. This is a very heavy process, so we do it after the program execution is complete. We do this in a different way for each the Ruby stack and the C stack. For the Ruby stack, it is rather easy. Method names can be obtained through C APIs, like RB profile name full label. And the same goes for line numbers. For the C stack, we have to use tools like editor line or dwarf information. But libbacktrace provides that for us, so we simply use that. So now we have collected the Ruby stack and the C stack. However, these are collected as completely separate stacks. So to make this very useful, we need to weave these together. So in reality, C comes first, then Ruby is executed, and then C comes again, and then now Ruby again. This is kind of hard, and I did this in a heuristic way. So this is the algorithm. We start from copying the bottom of the C stack, which is main. And we copy the C stack until we hit RBVM-exec, which is the function that starts the Ruby VM. This marks the start of the Ruby part. So now we can switch to start copying Ruby frames. Now, we need to switch back to C when we hit a cfunc, which is a function that is implemented in C. How do we know if a Ruby function is a cfunc? Ruby, as I said earlier, RB profile frames returns a callable method entry, which is something in C Ruby. It carries the information about the underlying C function. In the CME struct, it carries a cfunc struct, and the cfunc struct has a pointer to the C function address pointer. So in order to do this, of course, C Ruby doesn't want to do us to do that. So we do kind of cheat. I have copied some C Ruby headers into the PF2 to do this. And this is kind of a fragile implementation, but it works. We repeat this process until we consume the entire original stack, and now we have the full stack. The final part is visualization. This is the part that formats the profile into a good view. So visualization is important. Good visualization gives us many ideas. However, writing this kind of code is very different from writing profiling code, and I wasn't really good at that. So I decided to use existing visualizers. In this case, I chose, well, we have several options, but I found out that the web browser's developers want the work hardest on profilers, so I decided to use the Firefox profilers as just a visualizer. So wrapping up, profilers need to cooperate with runtimes, which is CBRE and the OS kernel, to collect information. And accurate scheduling is the key to controlling the balance between information and overhead. And unwinding is a heavy process, and it's done separately. As for the final part, I'd like to talk about the future of Ruby profiling. As long as Ruby continues to evolve, its profiling features shall also continue to evolve. because we need to profile weird code. So profilers are closely tied to runtime implementation. The weird code we saw in the morning was used vectors, but so profilers need to be capable of profiling vectors. And the language implementation keeps changing, so profilers need to catch up. Since profiling is so tied to its target, maybe more of the profiler should be moved into Ruby itself. Well, I don't know what the Ruby developers think of this, but Node.js and Go have the profiler fully integrated into the runtime. So maybe that's kind of a realistic way to do this. Software profiling is a never complete art. For example, recently, the demand on something called always-on profiling, which is also known as continuous profiling, is emerging. So we need to keep lowering the overhead to do this. So let's build a future together. Finally, I'd like to address some acknowledgements. Work on PF2 was supported by the Ruby Association 2023 grant program. And I'd like to thank Kokubun-san, my mentor, and Koichi-san and Mame-san, which gave many valuable advice to me. So that's the end. Please try out PF2 and give me feedback. Andポーク卵おにぎりもよろしくお願いします。